Hello! Today is Wednesday, April 14th, 2021, a day that will live in history. And this is Digital Image Processing 1, ECE 637. And today we're going to have to pick up the pace, it's my fault, on color imaging, okay? So we always kind of bog down a little bit at this section, I feel like, because this material is pretty interesting. So I tend to, it's kind of beautiful how it all fits together. So color space transformations, okay? So now you understand about colorimetry, you understand what the tristimulus values are, you understand what the color primaries are, okay? So what if you have different color spaces? So in one color space might be like the NTSC color space, which isn't used very much anymore. Okay, the color space is specified by two things: the color primaries, okay, and the white point. If you know the color primaries and the white point, you know everything about the color space, okay? At least if you're assuming you're doing a linear version. If it's nonlinear, then you have to know what the gamma is, okay? But so we told you this is the D65 white point. This is the equal energy white point. And then somewhere in here, I had the color primaries for NTSC. Chromaticity diet, hold on. Color primaries. I think, okay, one here. Do you know what page it was on? Oh, here it is, color primaries on the previous page. So let me keep these out so I can refer to them because okay, so here is these are the color primaries for different standards. This is NTSC, which isn't used that much anymore. PAL, which is the European version of NTSC, or NTSC is the US version of PAL. And then this is the 709 color primaries, which are, I used to say these were totally the standard, except for now where they're going to a lot of HDR stuff, so those have different color primaries. I'm not actually that familiar with those standards. And then these are the common white points. Equal energy white point, which is never used, but it's a sort of an important reference point. Okay, D65, which is by far and away the most commonly used white point. And then here's the C white point, which is the C illuminant. The C white point was part of the standard for NTSC. So it's not really used for anything except for it's baked into some of the standards we'll see. So you need to know what it is, okay? So, okay, fine. So I'll put this over here so we can refer back to it. Okay, so let's say you have data that's in NTSC. Okay, so we want to get, so the idea is this. The way you do color transformations is like this. So you might have over here NTSC, right? Or we'll have another thing, sRGB, which is the most commonly used one. You might have PAL. So if you want to convert between these, what do? Well, you could have and then you may have like an HP printer. So the HP printer may have its own color space, okay? That's not, usually these days everything comes from sRGB, but or you might have a camera over here. And the camera might not use sRGB. There are actually other RGBs that are, like there's an Adobe RGB that has a wider gamut than sRGB. So there are other color spaces, and it might just be device dependent. Not so much these days because everything's got hardware, computers in it, and then they do their own transformations inside of but the display, it used to be that you'd have a display, and the display with its primaries might vary. So you actually could measure them. And then, so it would be a device-dependent color space. So you don't want to have to, and you might have to, you don't want to have to do, if you end devices, then you'd have to have all unique pairs, which is N choose 2. N choose 2's n times n minus 1 over 2. So it's roughly proportional to n squared. So if you have, I don't know, 8 devices, then you 8 times 7, what's 7 times 8? 56, right? Divided by 2 is 28. You'd have to have 28 transforms, right? So that's not so convenient. So what you do instead is that you have an interchange space, okay? And the interchange space is usually x, y, z. It can also be a thing called LAB. We'll talk about that later. LAB is sort of essentially, it's based on XYZ. The problem with XYZ is linear in energy. And from the exam, you know that if you have something that's linear in energy, what do you have to do?
Gamma correct it.
Excuse me?
You have to gamma correct it to get rid of contours and the
Yeah, right. Well, you could do that, but if you don't want to gamma correct it, what do you have to do? You have to use floating point precision, right? So that's expensive in hardware and storage because it's 4 bytes for every component rather than 1 byte. So it's a factor of 4 more data and hardware, right? So you don't. So okay, but in principle, at least XYZ, that's fine. But if you're going to use XYZ, you have to use either floating point or you have to use fixed point arithmetic to high precision. 8 bits not good enough, okay? But anyway, so like if you have an ASIC, you might do a fixed point arithmetic because it might be cheaper to do the fixed point multiplies than a floating point multiplier. Although these days, floating point multiplies, you know, if you have like an ARM chip, I'm not really an expert on this, but you have an ARM chip, you know, I think you can pretty much do whatever you want. So you use this as an interchange space. So basically, if you know how to get to this space and back from this space, it's like the hub and spoke system for the airlines, right? Like everybody goes through Atlanta, right? So this is like Atlanta when you're traveling on Delta. So what I'll do is I'll explain to you how to get from whatever color space we're in, like say NTSC, into XYZ. So here, okay, now, so the transformation from RGB to XYZ. Now let's say RGB are linear, and let's not worry about white point right now. So what'll happen is that if I only turn on R, right? So I have XYZ, okay, and that's equal to M times 1, 0, 0. Because I'm only turning on the red primary, right? So when I multiply this matrix by this, I'll pick off the first column, right? So the first column, it'll be like, so this first column, what does that first column have to represent? Well, the first column was going to be, okay, what's this first column going to represent? Because if I only turn on the red, it's the only thing that comes out, right? So what does this first column represent? It's the red primary, because it's the color you get out if you only turn on the red, correct? So it's the red primary in XYZ coordinates, correct? Now, the primary for red is specified in chromaticity. So let's say, so here we want to convert to NTSC, okay? We want this in NTSC. So this is the NTSC color primaries. Now, they give you the chromaticity, which is 2 of the 3 numbers. The third number you can get by taking 1 minus the sum of these 2, right? Because they have to add up to 1. Now, okay, that's fine. But now, you're not really representing the brightness. So these value of the primary could be multiplied by any positive constant, and it would be fine, right? So, so the point is that the first column needs to be the color primary. So the color primary here for red for NTSC is 0.67, 0.33. Then the sum of these two things is what? That's 1, carry the 1, 1. Okay, so the third thing's 0, right? But it can be multiplied by any scalar constant, because any positive scalar constant, because you don't know how bright the primary is. It might be bright, it might not be so bright, okay? So you multiply by alpha 1. Remember, if you multiply by a diagonal matrix, what it's going to do is scale each column of this matrix. So there's some undetermined scaling constant, alpha 1, alpha 2, and alpha 3, which might multiply these color primaries, and that would still be fine, okay? So the second one is 0.21, 0.71. The sum of those is 0.92, so the z value will be 0.08. Got that right. And this is 0.14 plus 0.8 is 0.42. I'm sorry, 0.22. So that's going to be 0.78, right? So this is the blue color primary. And notice the blue color primary is strongest in the z component, which makes sense. The green color primary is strongest in the y component, and the x color primary, the red color primary is strongest in the x component. Okay, so and then there's 3 unknown constants here. Okay, so now so that's fine. So now, okay, so that's fine. So you know that M has to have this structure, but now there's 3 unknowns. So how do I determine those 3 unknowns? The 3 unknowns I can determine by adding the constraint of the white point. So the white point says that if I take M and I multiply by 1, 1, 1, okay, that I should get out the color that I'm determining is white. In this case, we're doing equal energy white. So equal energy white in chromaticity coordinates is 1, 1, 1. You normally list it as 1. Actually, it would be 1/3, 1/3, 1/3. But since this has the correct chromaticity, but you want the output scaling to come out so that it achieves the maximum value of 1. Okay, that's sort of just an arbitrary choice. If we were doing this in different circumstances, we might want this to be 255, 255, 255. Okay. So now if you plug in M, you plug in this matrix here, you multiply by 1, 1, 1, then you get alpha 1, alpha 2, alpha 3. Because if you multiply this diagonal matrix by the matrix 1, 1, 1 on the right, you get alpha 1, alpha 2, alpha 3. So you get this. So you have this equation. This is an equation, right? Because I could rewrite this 1, 1, 1. I have an equation there, right? So I can solve now for alpha 1, alpha 2, alpha 3. What I do is I take this matrix, I invert it, multiply on the left here, and I'll get the following answer. You could verify that. And then I plug that in, and then this gives me the final matrix. So that's how I found the linear transform matrix that gets me from RGB to XYZ under the constraint that I'm using the NTSC color primaries and equal energy white point. Does that make sense? So now, I could do the same thing with NTSC color primaries and the C white point. The C white point, if you recall, is defined here. Nominally, you would expect white to have chromaticity coordinates of about 1/3, 1/3, 1/3, because that's what equal energy white has. But then the different whites will be a little bit different. And this particular white, that's what it is. So now what happens is that, okay, in this case, I write these chromaticity coordinates for the white point here. Okay, because that's these numbers, 0.310, 0.316, 0.374, 0.310, 0.316, 0.374. Now, there's a normalization factor. In this case, they're not all one. So by convention, we normalize by the center component here, which is y. So you want the y component to have an output of 1. Okay? I mean, it's just a convention. So there's 3 unknowns. The white point is defined by 2 values, right? It has 2 degrees of freedom because the third one you can determine. So you have 3 unknowns. You need 3 measurements, but you do have that because you have 2 measurements for the white point, and you have this arbitrary factor that you normalize by y. And then you solve for alpha. You get these numbers. You plug them in, and this gives you the n. So you have a slightly different matrix for these 2 cases. And this becomes the transformation from RGB to XYZ, same color primaries, but a different white point. All right? So that brings us to something which used to be new, but now is old. The International Color Consortium defined the thing called, the ICC defined a thing called the sRGB, and it was originally implemented in a thing called Apple Color Sync, which I'm not even sure exists anymore. It's basically baked into the operating system. It's a color management system that runs on like Mac and Windows and probably Linux now, and makes sure that when you print things, that the photo you look at on your screen prints out to be the right colors. So to do that, you have to do the color management because you have to know what the screen color space is. You have to know what the printer color space is, and you have to convert between them. Okay. So to simplify all this, in the early days, they were like, oh, well, we're going to have a custom transform for everything. Well, inside the printer, the manufacturers implement custom transforms to make sure that their printer looks good when you print something on it. But these interchange spaces, ideally, you'd like to have these all be like custom because we'll see that you get gamut clipping. But in practice, excuse me, I'm sorry. I got my second COVID shot yesterday, so I'm good. Okay. And by the way, I had no reaction, or very little. Oh yeah. So ideally you'd like to have custom transforms because you would, but the convenience factor is overwhelmingly dominant. Okay. And what happens is that people don't want to have to deal with all this color space transformation stuff. So everything is. I would say 99% of all images are transmitted in sRGB. So if you download a picture from the web, or there's some JPEG in your when you get the JPEG off your camera, or pretty much any place you would get an image, it's almost always in sRGB, a standard RGB format that we're going to talk about. There are exceptions because, for instance, if you have a good camera or even a moderately good camera, you can go and probably work down the menus and select other color spaces for your images. Like there's a thing called an Adobe RGB I just mentioned. You can also shoot in RAW format, okay, which is the best. Or, there are other options, but how many people go in and configure their camera to use a different color space? Anybody's? Oh, we have one hardy soul here who's actually done it. Which color space do you usually use?
I usually save the images as RAW format.
RAW format. If you're going to do anything, that's what most people would do because you may as well go for the gold, right? I mean, just get the best. If you keep RAW format, you've got all the data, okay, and then you can do whatever you want. But then usually, the problem is RAW format tends to be device dependent. I think it's usually device dependent. So then you have to have a piece of software from the camera manufacturer typically, or you can get a third-party piece of software and configure it for your particular brand of camera. It has to be your particular brand and model of camera because it has to know what color space the RAW format's in. And then that's great because you could take that in that application and say print it on a printer and maintain the color space. But if once you go outside that application and you store it, now you've lost fidelity. But so most people, for most applications, yeah.
Yes. What color space the raw format maintain?
So the raw format is in the native color space typically of the actual sensor device. So if the sensor was trying to match XYZ, for example, it would be approximately XYZ. But here's the thing, the sensors don't match XYZ. So because the manufacturers, all you have to do is collect the data in a color space, which is basically in this three-dimensional linear space, right? You have to span the same subspace. So it has to be a linear transformation of XYZ. Any linear transformation will do. So the manufacturers will, so there's cost associated with having more accurate sensor response, right? So it's a cost optimization problem. You get the most accurate sensor response you can for the quality of the fabrication process you have, okay? And then what happens is, so 1 degree of freedom you can exploit in doing that design is you can do some linear transformation of XYZ instead of XYZ exactly. So they always would, because they want to get the best quality image for the least cost. And then once it's collected, then they transform to whatever color space they're going to use. But if you use raw, then of course you maintain all that information. But the problem with it is it's totally device dependent. So you have to know exactly what camera you have. And you might even want to do calibrations beyond that, like the camera can be like the problem is that they do a nominal calibration for that model of camera, but there'll be variation from device to device, right? So if you really want to be precise, you'd have to calibrate further. But most people just snap a picture, and go, oh, and email it to their friend, right? Well, when they email on an iPhone, of course, they're probably using a lot of new standards. But in the old days, if you just send somebody a JPEG, okay, it's going to be an sRGB. Okay, but the newer formats will be in other things. So the sRGB, while imperfect, has served people well because it's been used a lot for sending color images to people. And I want to also point out that it's interesting, JPEG, the original JPEG standard, when it was done in like the early 1980s, and I knew some of the people on that committee, that they didn't, at that time, the digital imaging community wasn't super color savvy. The video TV community was more color savvy. So when they defined JPEG, they didn't specify anything about the color space. So JPEG is color space agnostic, okay? It doesn't know anything about color spaces. All it knows is that you send 3 unsigned characters for RGB, and it actually does a color transformation to compress it, but when it's uncompressed, it comes out as 3 unsigned characters. But you can store anything you want in those. But the practical reality is that, like I said, 99% of the time, people use sRGB as the color space for JPEG. So, and what is sRGB? sRGB is basically, so it was a joint standard basically by Hewlett-Packard and Microsoft and the ICC organization. Basically, a few of the major commercial players got together at the time. HP made a lot of printers, and Microsoft had a lot of computer operating systems, right? And they got together and they agreed on a standard, and then they set up a standards body, sort of adopt their standard essentially as an open standard. And then, so it defines a color standard space, and it's basically 3 components. It uses gamma correction with a gamma 2.2, but the precise transform I'm going to explain is not exactly what I've told you previously, so I'll give that to you. It uses the 709 color primaries, which are here. That's these. These are the 709 color primaries. And it uses the D65 white point right here. So you can calculate what the color transformation is from that information. So you can, okay, so if you're so I'll first explain how to convert from sRGB to XYZ, and then I'll explain how to get from XYZ to sRGB. Okay. Okay. I'm going to start off by not. Okay. I'm going to start off by giving a fib, telling a fib. Okay. I'm going to pretend this is true, but it's not true. Okay. I'll come tell you what is true later. So, R tilde, G tilde, and B tilde are the gamma corrected sRGB values. So the first thing you have to do is ungamma correct them, right? So you divide by 255 because they're usually assumed to be unsigned characters, and you raise it to the 2.2, okay? That removes the gamma correction. Then these values have to be stored with what kind of data type? Excuse me? Floating point, or you'll get contours in the dark regions. I felt like I was honorable. I had to add that answer for the last question because I thought you guys it would be unfair if I didn't give you credit for that after I filmed. So contours in the dark regions, right? So now, okay, fine. Now once it's at a linear coordinate, now you have to transform from RGB to XYZ. So it's the same drill, okay? You need to find this matrix M now because it's a linear transformation. You can solve for the alphas, and this is the equation. This is the D65 white point. Here I've normalized by the Y value so that the center value is 1. And what do these columns, how do I find these columns? What's that column? Someone tell me so that I know you're paying.
XR, YR, GR.
Yeah, these columns represent the color primaries, right? So this would be the chromaticity associated with the red color primary for the 709 color primaries, okay? And you can read them off. They're right here. You see, 0.64, 0.33 is 0.33, and 0.03 is 0.03, okay? I'm not telling you a lot, okay? So you solve for the alphas, you multiply through, and this gives you M. So this is the transform from sRGB to XYZ. You know what's kind of cool? You can actually Google this, or you used to be able to Google it. I'm sure you must still, but I haven't done it for a while. And you can find an online web page where they tell you how to do the sRGB to XYZ transform. And they'll list this matrix out. Okay. And it's exactly this, like to the every digit, okay? So it's kind of it builds confidence that you can derive this transform all by yourself. You know, it's the thing. If you look it up in the standard, they'll have it there, but you can derive it from the base principles. It's kind of reassuring, you might say. Of course, okay, I lied here because this is actually the approximate sRGB. The M matrix here is exact. But what's not exact is this, okay? Because I'm not telling you the truth. But I'll get back to that, okay? So now let's say I want to go the other direction. I want to go from XYZ to sRGB. So I can take the XYZ values and I can compute the linear RGB values by multiplying by the matrix inverse. So I can invert this matrix here in MATLAB, and I get that matrix. This matrix now has negative values in it because, you know, there's issues with the XYZ gamut. Like if you take the entire XYZ gamut, a lot of it falls outside of the real color space. You get imaginary colors. So if you do this transformation, you might get RGB values that are negative. Now, they could be negative for two reasons. One possibility is that the color just can't be displayed with these color primaries, or it may just not be a legit color, okay? Like it's an imaginary color. And now once I have the linear RGB, I can gamma correct the linear RGB to get the gamma corrected RGB, okay? Now, if you actually ever have to calculate sRGB and XYZ, which you very well may, because if you need to, like, let's say you work for a company like Apple, and you're developing some algorithm to denoise the image or to enhance something or whatever, you'll usually, it's not uncommon that you would have to take the image into color space, convert it to some kind of other coordinates, process it, and convert it back. So you make sure you have to do that correctly, because if you don't do it correctly, you'll screw up the colors in the image, okay? And if you screw up the colors in the image, people will be very unhappy. They won't like the quality of the image. Also, you might introduce false contours, which is the other thing. So don't ever do this, okay? Because this is actually wrong. It's wrong. It's not the true standard. So the true standard, which I've kind of protected you from because I was afraid to tell you about it, is a little more complicated, okay? So, and it has to do with a lot of weird historical reasons. In the old days, they couldn't implement power law functions like cube roots really accurately because they had to do it with actually analog components. So there were kind of odd offset things and so forth. So they came up with this kind of alternative transform, which was sort of an approximation to the power law, but the problem is that with the power law, when you're taking like x squared or x cubed, if you're taking, say, the cube root, you get a function like this. The derivative here is really high, and that can make the electronics unstable if you try to do it in analog. And just in general, there could be issues because if there's for some reason introduce a small offset into your image, then you could get a lot of you get a big error in the tone. I mean, it's not such an issue today because everything's done digitally, but when things were analog, you had old TV sets and you had to adjust the brightness and the contrast. This caused a problem. So what they did is they had this kind of thing which is softened. The derivative is sort of limited for small values. So this is the exact transform for gamma correction. Notice that instead of dividing by 1 over 2.2, you're dividing by 1 over 2.4. But that's compensated by the fact that you have this little offset. And if you check this thing, to the precision of this calculation, this function is continuous as a function of x. So this is kind of a piecewise, partly linear and partly power law fit to this function, okay? So if you're going to implement, if you're going to convert from XYZ to RGB, then the matrix transform is correct. But to implement the gamma correction, this is the actual function you're supposed to implement. Don't do the other one. The difference between this exact calculation and the approximate one is quite significant, okay? The other one's perfectly good conceptually, but the colors will come out wrong, okay? It's unacceptable from a commercial implementation standpoint, okay? And then this is the inverse relationship. And this inverse relationship is exact, or it's very close, okay, to the number of digits of precision here. It gives you the inverse, okay? And so this is what you want to implement for the exact sRGB to XYZ transform. So this does the D-gamma correction. This removes the gamma correction. It un-gamma corrects. And then you do the linear transformation to XYZ. Okay? Any questions about that? So these are good to refer to if you ever have to implement those things. Yeah?
So is this kind of gamma correction specific to sRGB only? So like if we had a different color space that we wanted to go back and forth with XYZ, we would be using this same function, or would we be doing a
No, it's a good question. Basically, basically, the answer to your question is that this is what, whenever someone says gamma correction, this is what they actually mean. Okay, so if you're doing gamma correction, you never do the thing I explained up to now. Like, I know I spent a lot of time explaining this, but the thing I explained was systematically wrong. Okay, Just do a global replacement of what I told you to do before with this. But the other thing I told you to do is the simplified thing is fine conceptually, and as long as you're sort of working within your own world, it's okay too. Okay, but if you have to communicate with anybody else, don't do it. Okay, because it'll be completely wrong, and it'll be kind of one of those things where things will be off just a little bit, and you'll be having trouble debugging it, tracking down the problem. Basically, anywhere where the concept of gamma correction is used, this is how it's done. It's a good question. And as a matter of fact, I'm going to hit that in just a minute. So, analog NTSC. Analog NTSC, the only thing that anybody uses analog NTSC for anymore is that I can think of is what? I'm thinking of something. I don't know. Can you guys think of anything? Is there anybody in here who can think of what analog NTSC? Does anybody know what analog NTSC is? Like, that's like TV, right? Analog NTSC, where you have like broadcast television. You put an antenna out, and it's not decoded digitally. Does anybody have an analog TV? Okay. I have a bunch of analog TVs in my basement. You know why? They're called drones. You know those little drones you fly? Okay. They're all analog NTSC or PAL. Okay. So it's the last bastion of analog video. Does anybody have a drone? Oh, they're fun. Okay. I don't know if I haven't flown anything recently, so don't come out to arrest me. Because I know that they've changed the rules for the, the FAA. Okay, because I have to review what it is. But actually, if you buy like a DJI, some of the new DJI drones, they actually have digital video. But the digital video is still not preferred. Oh, I know there's something else you guys must use analog TV video. Oh, come on. I'm sure somebody in this room must use it. Video games. How many people are serious video gamers? Okay, does anybody use analog TV? Like serious gamers use analog TVs, right? Does nobody else know this?
We don't have time for games.
Yeah, I know. You guys are working night and day doing your thesis research to make your advisors happy, okay? But how many people does anybody know about this? That serious gamers use analog TVs? Why? It's lower latency, right? That's why they use them on drones too. Because the drones, the digital video, first of all, encoding digital video is slow and computationally expensive, but it's also high latency. So they have low latency downlink for drones now. But it's expensive and it's complicated. I think at some point it'll probably displace analog, but the analog's holding on. They're holding on like the superhero from the cliff, for dear life. So there's still a role for analog NTSC video, and PAL's pretty much the same. One of the big differences between PAL and NTSC is 60 hertz, and PAL is 50. Okay, by 60 hertz it means you do 60 fields per second, but you do 30 frames per second. So a field is either the odd or the even line. So standard NTSC video uses 480 lines. Okay, 480 lines, and then so it's like okay, and then. So the red would be one field, and the black would be another field, okay? And then there would be 480 of these lines total, and half of 480 is what? 240. There'd be 240 lines for each field, and then it's interlaced. So you do one and then the other. Interlace means you alternate. So they did that because it saves like bandwidth basically that to do everything, because you can do 60 hertz at 30 hertz you can see flicker, but since you're doing every other line, you don't notice it for most content. But it does, but now with modern TVs, pretty much they've gone to all progressive scan instead of interlay scan. It's a little less efficient, but it's better. It's easier to process basically, and you don't see flicker on if you have like text and it hits the edge of a line here. On the interlay scan, then the edge of the text is going to get updated only at 30 hertz instead of 60. So you'll see the edge of the text flickering a little bit if you have an interlay scan. These days they do 120 for the digital TV. They do like 120 frames per second at like progressive scan. So sometimes that's interpolated, and the raw data rate is 60 frames per second, and sometimes it's actually true 120 hertz. But to do the 120 hertz, you need a special HDMI protocol that can handle the additional bandwidth, especially if you have 4K TV. I'm going off into a tangent, but it's sort of interesting. So anyway, so here's the thing. Now, if you read off, this is kind of cool. Oh, yes. These old standards die hard. So this is the S. Okay. If we go back, this is the NTSC with the the NTSC with the CY point. Here's the NTSC with the CY point, right? So this is the transform from RGB to XYZ. So if you look over here, this is the matrix M we calculated. So the center row of this matrix represents the transform from RGB to Y. Okay. So Y is like, okay, when they back when they had color, okay, when I was a kid, they didn't have color TV. They only had black and white TV, okay? And they only had, by the way, like 10 channels, okay? And that's why you had ABC, CBS, and NBC. There was no PBS even, okay? That was a little bit later. So they had, so they had black and white TVs. So now how do you make a achromatic image out of a chromatic image? Well, they just took the Y. Actually, they started off with the black and white TV, and then they added color. They had to make it backward compatible. It's really interesting how that happened, but I won't go into it because I'll be here forever. So, but the Y here is basically the black and white component of the color television picture, okay? So Y is sort of, you might say, the luminance component, right? So if you want to compute Y, using the NTSC color primaries in C, you just multiply by this center row. And guess what? That's exactly what this is. See, I kid you not, because this is 0.2990, 0.2990. It's 0.5864, 0.5864, 0.1146, 0.1146. See, I would have been really embarrassed if it turned out that was wrong, but it actually was correct, right? So I read that off. So if you look this up, this is the official transform you use to get from RGB to Y, okay? But what's really funky, first of all, this is assuming NTSC color primaries and a C white point, but nobody uses them anymore. And what's really funky is that they go, well, it's good enough. We'll just use the gamma corrected values, okay? This is supposed to be linear, but they just throw the gamma corrected. They go, it's good enough, okay? And it's this crazy thing, Y tilde or whatever you want to call it. So that Y tilde thing turns out to play an important role in the encoding of TV video. So, so you compute that Y from, and so in this case, these RGBs could be whatever. They're usually sRGB, gamma corrected sRGB, because that's what the TV sets use, at least they used to. And then you send, there's a thing called YPRPB. This is analog. If you have an old like a CD player that's still analog outputs, it'll have outputs on the back where you can plug in the RCA cables. You know, the RCA connectors are the little coaxial connectors that plug in for analog video. And it'll have, you'll see, it'll say YPBPR, okay? That's what these things are. They're actually analog signals that you plug in. It's kind of cool. Now, there's another thing then, you go, okay, it gets weirder. You can take these things and you normalize them by these crazy numbers that they picked at the beginning of time, and you get a thing called YUV. This is still analog. And then you do this crazy transformation. Somebody decided 33 degrees was exactly the right number, and you get a thing called YIQ. It's still analog. Then what happens is they use, the YIQ is what they actually encode on the NTSC video. Okay, so this is what's actually transmitted. So if you get terrestrial broadcast, did they stop doing terrestrial broadcast? I think they may have. I don't really know. In any case, if you have a drone, this is what gets transmitted on the RF signal. YIQ. I and Q actually get modulated as analog signals. You say, well, how do they send the Y and the I and the Q all at the same time? They do this really clever thing, okay, that there's not time to go into. But they do a thing called a comb filter, and they take advantage of the interlacing, and they do this frequency shift, and they put the signals between each other, okay, which is why in the old analog TV sets, if you have for high frequency content, you would get color rainbows, because the high frequency luminance component would bleed into the chrominance component. Okay, so that's this, and then there's these issues and so forth. But this is the part you actually need to know, because data will actually come in this format if you're doing image processing. So people will send you data. They'll often say, people will tell you, oh, I'm sending you, what will they say? They'll say, I'm sending you YUV data. They'll say, I'm sending you YUV data. Nobody ever sends you YUV data. They say it, but they don't mean it, because YUV is analog. So if they're sending you digital data, what they're really sending you is they're sending you YCBCR data, okay? And this is what is sent, this is what's encoded on a standard digital TV NTSC, digital NTSC color standard. So if you got sort of either standard definition or basic high definition without HDR, what they digitally send, or the other thing is that on a JPEG, this is what's encoded on a JPEG file. So if somebody gives you a JPEG, basically the encoded data on the color JPEG is YCBCR. So to get back from from gamma corrected RGB, you can get the YCBCR through this color transformation. You can just look this up if you ever need it. And then if you want to, then of course you can reverse that with these transforms, okay? And it's really funky because they have things like this where they have offsets. Now this offset's fine because it's 128, because you have this CB and CR is going to be a signed quantity. But the so offsetting by 128 makes sense because you're basically taking the unsigned int character and you're using it as a signed quantity. But this offset of 16 is just weird because you're just throwing away those quantization levels. This thing here, Y, can never go negative. But it's a holdover from the old analog TVs that they didn't have they needed a pedestal for the signal to be on, because otherwise they couldn't turn the transistor on, basically. Okay, I'm really running out of time. Okay, so well, next time I think we're gonna I think we went through all this. So that's it. I'm finished with color transformation. I think we'll try to move on to the next section. Opponent color spaces. I think maybe we'll have to skip opponent color spaces a little bit. Maybe I'll talk about it real fast next time. The big upshot with color spaces is opponent color spaces is that basically your spatial modulation transfer function for the am I here? Your spatial modulation transfer function for color falls off faster than for luminance. Okay, so that they take advantage of that, and they subsample the color for either video or analog or still images. They subsample the color by 2 to 1, and that reduces the amount of data you have to transfer. Okay. All right. See you on Wednesday. Thanks. Bye. Wait. Hold on. What's today?